Alright, hey guys, today we are working on Chapter 2, Sections 3 and 4, so let's dive right in. Chemistry of water. Water is a polar molecule. The shape of a water molecule and its polarity make something called hydrogen bonding possible. This is an example of a structure-function relationship. A hydrogen bond is a weak attraction between a slightly positive hydrogen atom and a slightly negative atom. It can occur between atoms of different molecules or within the same molecule. A single hydrogen bond is easily broken, while multiple hydrogen bonds are collectively quite strong. It helps to maintain the proper structure and function of complex molecules such as proteins and DNA. Here is a diagram of water forming hydrogen bonds. Okay, you will see that this oxygen has a slight charge that is attracted to the slight charge of this hydrogen of another water molecule. And this happens over and over and over and over again, forming multiple hydrogen bonds. Properties of water. Water is a water molecule. Water molecules cling together because of hydrogen bonding. This association gives water many of its unique chemical properties. It's also why water has a high heat capacity. The presence of many hydrogen bonds allow water to absorb a large amount of thermal energy without a great change in temperature. Those hydrogen bonds take that energy in. So the temperature of water rises and falls very slowly. And that's why whenever you fill up a pool in the beginning of summer, the water is initially very cold, but as the ambient temperature, the air temperature rises, eventually that pool water will warm up, but it takes it a very, very long time. The high heat capacity of water allows organisms to maintain their normal internal temperatures, protected from rapid temperature changes. We are composed of a large amount of water. This water helps keep our temperature stable because remember, if our temperature gets too hot, we die. If our temperature gets too cold, we die. We want to stay in that sweet spot, and that high amount of water that we have, that large amount of water, helps us keep that temperature constant. Okay, here we have an elephant with a woman sitting on his back playing in water. Okay, bodies of organisms cool when their heat is used to evaporate water. So whenever that water gains energy, it takes that energy from your body and evaporates, and it takes that energy with it, which is how you cool down. Here to the left, we have a graph showing temperature and heat absorbed. Okay, you'll notice that it takes a lot of energy to increase the temperature of water. Properties of water. Water has a high heat of evaporization or vaporization. Hydrogen bonds must be broken Hydrogen bonds must be broken to evaporate water. It takes a lot of energy to break those hydrogen bonds. Bodies of organisms cool when their heat is used to evaporate water. So whenever you get hot and you start sweating, whenever that sweat evaporates, it takes body heat, takes energy from your body with it. When it's very humid outside, it's harder for that water to evaporate. So you feel hotter when it is humid because that sweat on your skin can't evaporate. Another property of water is that it is a good solvent. That means that it is good at dissolving things in it. Water is a good solvent because of its polarity. Polar substances dissolve readily in water. So these are things that have a charge. Hydrophilic molecules dissolve in water. These are things with a slight charge. Hydrophobic do not. These are oils and fats. That's why oil and vinegar salad dressing, it separates. Because the oil is hydrophobic, whereas the vinegar is hydrophilic. Hydro means water. Philic means loving. Phobic means hating. So hydrophilic molecules love water. Hydrophobic molecules hate water. A solution contains dissolved substances or solutes. Water as a solvent. This is how ionic compounds dissolve in water. Okay, sodium has a slight positive charge because it has given away an electron, so it attracts the slightly negative region of the oxygen in this water molecule to it, and those slightly negative oxygens want to get close to it so that the charges even out. You'll notice over here with the chlorine, okay, it has a negative charge because it has an extra electron. In the positive region of the water molecule, these hydrogens, they are attracted to the chlorine, all right, and they surround it. Properties of water, slide 2. Water molecules are cohesive and adhesive. Well, cohesion is the ability of water molecules to cling to each other due to hydrogen bonding. Water flows freely, and this is why we have surface tension. Okay, that's why water striders, those bugs that skate on top of the water, that's how they can do that, because there's a lot of surface tension. Adhesion is the ability of water molecules to cling to other surfaces. Okay, this is due to water's polarity and something called capillary action, which we're going to talk about a little bit later. This is why water sticks to your car whenever it rains. Cohesion and adhesion account for water transport in plants as well as transport in blood vessels. So this is a diagram of a tree, obviously. So you'll remember that trees absorb water through their roots. Okay, then it clings to the sides, clings to the tubes inside the tree called xylem and phloem. Xylem carries water, okay, and it goes from the roots to the very, very tippy top of the tree. It's like a big, long soda straw. Okay, and because water molecules cling to each other, when one of them gets pulled up, the next one gets pulled up. Okay, it's like a giant chain. All right, there are openings in the leaves of trees and other organisms, and those openings, when they're open, water starts evaporating. Well, whenever one molecule evaporates, another one moves up to take its place, and it pulls all of the other molecules up with it. Frozen water, also known as ice, is less dense than liquid water. That's why ice cubes float in ice water. At temperatures below 4 degrees Celsius, hydrogen bonds between water molecules become more rigid, but also more open. They have more space between them. Water expands until it reaches about 0 degrees Celsius, and then it freezes completely. That's why if you freeze a water bottle that is completely full, it will bust, because those water molecules, they spread out, and they have more space between them, so it expands, and your water bottle will bust. Ice floats on top of liquid water. Like I said earlier, without this property, ice would sink, and eventually oceans would freeze solid instead of freezing from the top down. Okay, this ice acts as an insulator on top of a frozen body of water. So once it's frozen, it keeps the heat energy down below in. So here's a picture of some seals on a chunk of ice in the ocean. Okay, it is less dense. You'll notice up here that the water molecules, they form what's called a lattice structure. Okay, you'll see that there's a lot of space between those molecules, and they're not moving because they're frozen. Over here we have liquid water, and you'll notice that those molecules are a lot closer together. They don't form that lattice structure. Here is a pond in winter, so there's ice on top. Okay, remember it's less dense, so it's going to float. All right, and all of this living things down here, okay, that water is still liquid. They can still do what they need to do in that water. All right, section 4, acids and bases. Hopefully you remember from physical science that pH is a measure of hydrogen ion concentration in a solution. When water ionizes or dissociates, it releases an equal number of hydrogen ions and hydroxide ions. So basically that water molecule is breaking into two pieces. One of the pieces has just a hydrogen ion, and the other one has an oxygen bonded to a hydrogen. Acids are substances that dissociate in water, releasing hydrogen ions. So when acids break down in water, and they give off a hydrogen ion. Bases are substances that either take up hydrogen ions or release hydroxide ions when they are in water. The pH scale. The pH scale is used to indicate the acidity or basicity or alkalinity of a solution. Values range from 0 to 14. From 0 to 7, that is considered acidic. 7 is neutral, and 7 to 14 is basic or alkaline. All right, for pH, we're going to use the logarithmic scale. Each unit change in pH represents a tenfold change in the hydroxide concentration. So a pH of 4 is 10 times as acidic as a pH of 5. A pH of 10 is 100 times more acidic than a pH of 8. Okay, here is a diagram showing some common substances and their pH. All right, stomach acid is very, very acidic. Its job is to break down food, so you want it to be acidic. You want it to be able to break those molecules down. Lemon juice, about a 2. Right, bread and black coffee is about a 5. Rainwater is usually a little bit acidic. Milk is pretty close to neutral. Pure distilled water is a pH of 7. Human blood is usually between 7 and 8 on the pH scale. Baking soda and stomach antacids like Tums are usually somewhere around an 8 to a 9. Right, ammonia is very basic. It's usually somewhere around 11 or a 12. Oven cleaner, very basic. Okay, it's down here around a 13 or a 14. Right, we are going to be doing a lab tomorrow in which we look at the pH scale. So please come to school dressed in jeans and closed-toed shoes. Also remember to bring a ponytail holder if you have long hair. Oh, one more, guys. Buffers and pH. A buffer is a chemical or a combination of chemicals that keep pH within normal limits. These are what keep the pH from going too acidic or too basic. Health of organisms requires maintaining the pH of body fluids within narrow limits. Human blood is normally about 7.4. Okay, so it's not exactly neutral. If the pH drops below 7, acidosis results. If it gets above a 7.8, then alkaloidosis, sorry guys, having trouble with that word, alkaloisis results. Okay, it gets too basic. Both of those are life-threatening. You want the pH of your blood to stay right at 7.4. If it doesn't, then bad things can happen. Your body has built-in mechanisms to prevent that. Okay, your body contains natural buffers that keep that pH from changing too much. An example would be a carbonic acid buffer. It dissociates and reforms to reduce the pH. Okay, so a buffer is something that can accept hydrogen ions or hydroxide ions and keeps them from turning the solution too acidic. All right, and that is it, guys. So remember, lab tomorrow. Please come dressed appropriately. If you have any questions, feel free to shoot me an email.